Hi, welcome to the discussion on sail area analysis. So here we are in our design process. We have generated our concepts. We have selected one of the concepts from the 15 from each of our teams that we think we are going to use to build it. Now we're in the analysis phase. So last discussion we had was about the whole design, and the main focus of that was how to make sure that the boat would float at a specific height in the water. So when it would heel over because of the wind blowing on the sail, it wouldn't take on water and it would also remain stable in the water. Today we're going to talk about how to design a sail. So when we think about what we're trying to accomplish with the sail area analysis, it's important to think, what is the goal? What are we trying to, in quotes, hire this sail to do? What job do we want the sail to do? Well, we want the sail to propel our boat in the water as fast as possible. So if we think about it in those terms, what do we want to maximize? That's right, we want to maximize the sail area. We want as big a sail as possible so it can catch as much wind going downwind, and it can turn into an airfoil and generate as much lift as possible going upwind. And so we want to maximize how much sail area we can have. Now, what's the other side of this equation? What are we trying to balance out? So if on the one side we're trying to maximize it, make it as big as possible, what's the problem with making it massive? What might happen to our boat if we have too big a sail on it? I'm sure you've already thought of this, but it would tip over. So today's discussion is going to be around balancing that equation. And in engineering, there's always a balance between multiple variables. In today's discussion, we're going to be balancing how much sail can we get away with to get as much velocity out of the boat, and we're going to balance that with keeping the boat from tipping over. So first off, we talked about this before. We've got a moment, and that moment is generated by having a certain amount of force with a lever arm. So what's generating the force on our sailboat? Well, we've got our center of mass, which is pretty much the weight of the boat and kind of a center point of where all of that weight can be simplified down into a single point. And so we've got the center of mass, and so that's pushing down, pulling our boat down toward the center of the earth. And then we've got our buoyancy force, which we calculated out is all of the volume of the water being displaced here because of the boat. That generates a buoyancy force, which is pushing our boat upward. And so the center of buoyancy is kind of like the center of mass. We've got a single point here where we could resolve all of that force that is generated by the water pushing against the hull of the boat. It's pushing it in the upward direction. Now, the problem we have with that is that if we have those two working in the same direction, so if we just get a little bit of tip, this is kind of like having a pen stand up on its point. The center of mass is going to try to tip one direction, and then the center of buoyancy in this case is pushing up in that same direction. So it's going to help flip the boat over. You can see that here. As soon as it starts going, then it's going to be just like the tip or the pen of a tip. Sorry, the pen on its tip. It will just become unstable and tip right over. So what do we do with that? Well, we try to move this center of mass down so it's below our center of buoyancy. Now when it starts tipping, you can see they're working in opposite directions. And so the center of buoyancy is working in this direction, trying to pull it back upright, and the keel is working in this direction, trying to pull the bottom of the boat down in this direction. So that is why we have a that is why we have a ballast on the end of our keel of our boat. And so this ballast right here, or the center of mass, we move the center of mass by putting a weight down at the end and try to get those to work in opposite directions, so then it becomes more stable. So that's what our discussion is going to be about today. Before we get there, though, we probably ought to take just a moment to talk about coordinate systems once again. So the coordinate system, what we talked about last time, this E sub z, tries to help us keep track of what is the positive and what is the negative direction. So now we have unit vectors that there's three of them, and they're orthogonal to one another, and that's called a basis. And so our basis is this EX, EY, EZ. And so what we're looking for here is that this unit vector will help us keep track of what direction we've got positive and negative forces acting, and also moments. And so we'll talk a little bit more about moments in just a minute. So the point from which all distances are measured is called the origin. So we have the origin in the middle here. So that's going to help us keep track of how far down in this unit direction of y we're going, z, and x. And all these vectors must satisfy the right-hand rule. Now, how many of you have heard of the right-hand rule? I suspect, based on past experience, there's probably about 60% of you raising your hand right now in the comfort of your home or wherever you're watching this. Maybe it's in a library. So let's talk about the right-hand rule, just to clarify for those who maybe haven't seen it, or maybe to just clarify a little bit more for those who have seen it, what we try to do with the right-hand rule. So the right-hand rule is just a very simplified way of thinking about what are the positive directions. So if you hold your hand in this configuration, you can see that we have A, B, and then if we cross A and B, we've got this direction up here. In this direction, what we're going to talk about is this direction, this A cross B, is a moment. And so if you were to pull on B, it's going to rotate your hand around this Z axis. A cross B is going to be a moment or a rotation around this Z axis. And so that helps you understand which way is a positive versus a negative. So the reason it's not the left-hand rule is because we get one of these in the wrong direction here. We get a negative Z in here. So the left-hand rule doesn't work quite as well as the right-hand rule. All right, so when we're talking about a right-hand rule, one thing to think about is your perspective. Which direction are you looking at the right-hand rule for a positive or a negative rotation around that axis? And so if you were putting a screw in a wall and you were looking at the head of the screw, standing back, looking at the head of the screw, and you rotate and you twist your screwdriver, say you put a force on B, and so it rotates your screwdriver around the Z axis, that means you're going to have a positive moment that is putting that screw into the wall. So it's going to be going in the positive Z direction because you're putting a rotation on it by doing a force. You're applying a force to the end of B. Hopefully that makes sense. So you're rotating it around your thumb, which would be the Z axis, and so you're rotating it in, so that's a positive. So if you're looking at it and you step back again, look at the head of the screw, if you look at it, that is actually going clockwise. And so this is where a lot of students, I think, get confused, is when they're looking at a piece of paper and what, are they looking at the piece of paper from that perspective like you would be looking at the head of a screw, or are you looking at it from the other direction? Now, what does that mean, the other direction? Well, if you look at the head of the screw and say you're on the other side, so now you're kind of on the other side of the wall and you're looking back at that screwdriver, the screwdriver looks like it's rotating the opposite direction, and that's still going to be a positive moment. So using the right-hand rule will help you understand if it's a positive or a negative moment. Hopefully that makes sense. Think through it a little bit, maybe look at some YouTube videos. I don't know that the right-hand rule is majorly critical in a lot of application. However, if you want to figure out which way something is going in a positive direction, it is pretty helpful for that. So I wanted to make sure that everybody kind of understood what that right-hand rule was before we moved on. Okay, so now let's talk about moments. A lot of people, and you can think of moments like a torque, right? We're putting a torque on something, or we're putting a moment on something. And so moment is due to a force. And so if we apply a force to a member and there is a fulcrum point or a rotational point, the distance away from that rotation point where we apply the force, that distance times the force is going to give us a moment. So how much torque are we applying to this point here, or how much moment is being generated? So you can see this flat teeter-totter looking thing, just we've got a beam sitting on top of a triangle, and it's rotating about this point. And so we've got this mass sitting here, which is causing a force to be applied to this side of it. Obviously, if there's nothing on the other side, this is going to move down. But before it moves, and we can calculate out what that moment is generated by this mass, this block sitting on this member. And so it's actually R, which is the length away from that rotation point out to the line of action. So if we have our moment out here, we've got this line of action that's moving through this mass in this direction. So it's perpendicular. You see that perpendicularity is important because this R cross F would have another component to it based on trigonometry if it was not a straight line through there. And so what's important for us to take away from this discussion today and relative to our boats is that the line of action is a perpendicular line, and the distance away from that line of action to our rotation point is the length of that moment arm. So we've got a force times a distance is equal to our moment. Okay, so now if we apply this here, we can look at that and determine that this is Euler's law, or sorry, Euler's second law. We can determine that if we have this distance, m times r, that's going to be equivalent to having twice the mass in a closer, with a shorter moment arm. So if you think about this, it makes pretty good sense, right? If you tried to balance your pen on your finger, it's likely that if it has like a grip and a few other things, a spring, some other stuff like ink at the end of one side, it's the actual balance point is going to be a little bit offset from the center line of that pen. And that's because you have a little bit more mass out there. So in order to have these be equal, you've got to have a shorter moment arm. So this twice the mass times this moment arm is going to be needed. You're going to need to divide that moment arm by 2 in order to have the mass times this moment arm equal that. Okay, so let's take a step back and look at the big picture. What are we trying to do with the sailboat? Well, we want our sailboat to float first, and we figured that out last time. Now we don't want it to flip over in strong winds. So that's what we're going to work on today. We're going to figure out how to do an analysis to determine what's the biggest sail we can get away with without having our boat tip over. So let's do the sail area analysis, kind of like what we do with our homework. You can see the sailboat, our design requirement. The sailboat shall maintain an angle less than 30 degrees. So this has been imposed upon you by your customer. Customer says, I don't want it to tip over more than 30 degrees because I don't want this to happen. I don't want water inside my boat. From the vertical, in wind speeds up to 10 miles per hour. So down in our regatta pool area, which you've all visited now, we have those fans set up. So we'll have around 10 miles an hour max wind velocity. Now, keep in mind that there are areas in the pool where it's going to be much, much lower than that. But this is the max. So this is the worst case scenario. So if we get right in front of one of those fans and our sail is fully extended and it's catching 100% of the wind coming out of that fan, our boat won't tip over greater than 30 degrees. Now we anticipate our boats will keel over, and so they will have this angle theta right here. They will be tipping over, but we want to make sure that in the max scenario where it's catching all of the wind from the fan, it won't go greater than 30 degrees. So what is our source? Well, in order for the design to be competitive in the regatta, the design must be capable of staying upright in wind speeds of 10 miles an hour or greater. So what's our verification strategy? We've talked about this before. Prefabrication, we're going to verify that we are making this requirement by doing a sail area analysis to determine what's going to happen. Now, what about post-fabrication? How are we going to verify post-fabrication? That's right. We're going to put it in front of a fan and make sure that it doesn't tip over greater than 30 degrees. And so that's actually part of the test that we will do near the regatta time. Okay, so let's look at some of the variables that we have to deal with. We've got some dimensions of our boat, and we're going to use those dimensions to have the maximum area of the sail, or A sub S. That's what we're trying to calculate out today. What are some of the other design variables? Well, we've got the height of the keel, so that's this right here. So from the bottom of the boat down to where our ballast is. We've got the hull height itself, and so you as the designer have control over these variables, and so you can update your calculation sheet based on what variables you think are going to work best. And this is why I stress all the time that it's very important to me that you learn how to put this into some sort of software package like Excel or SMath or MATLAB, is because it's super handy for you to be able to change these variables and see what happens to the variable of interest, or the sail area in this case. So we've also got our mast height. Like the mast height is going to go from the top of the boat all the way up here. And we'll talk about why we're looking at a third of the way up in a little bit. And then we have these other variables here where we go from our rotation point out to where a force will be applied on both sides, on the ballast and on the sail itself. So let's talk through this. So we're assuming that our boat is stationary in the water, and so we're trying to maximize the sail area based on our boat being in a static position. So we're going to say we've got a force generated by blowing 10 miles an hour of wind on this side, and then we're going to have a force due to our ballast, the gravity on our ballast. So what do we need? Well, given that the boat is a stationary in still water, determine the maximum area sail area, and design in order to have the boat maintain an angle of less than 30 degrees. So our theta is going to be 30 degrees from the vertical at a wind speed of 10 miles per hour. Okay, so what do we know? Well, we know the acceleration due to gravity. What's that? What's that number again? 9.81 meters per second squared. The wind is traveling parallel to the surface of the water with a maximum speed of 10 miles per hour, which is equivalent to how many meters per second? Now, the reason we're doing this unit conversion is to make our units match when we put it into our equation. So if you remember doing our unit conversion, this is how I like to do it, where I put all of the different conversion factors in this form. So then I can look at my units and cancel my units out as I'm going through this analysis. So our acceleration due to gravity is 9.81. Our maximum speed is 10 miles per hour, which is equivalent to 4.47. So the way I came up with that 4.47 is I did a unit conversion. So I had 10 miles on top per hour. And then I converted the hours first, and so I can cancel my hours to here because there's 60 minutes in 1 hour. So I cancel my hours, and then I put 1 minute in 60 seconds, cancel my minutes, and so now I'm left with seconds on the bottom. And then my miles, I can do this conversion of 1609.344 meters per mile. Now, I think I've mentioned this a few times before, that in my mind, I try to keep track of the 2.54 centimeters per inch. And so I could actually do that analysis. I would just have several more lines out here to convert my miles into feet, 5,280 feet, and then from feet to inches, so 12 inches in 1 foot. And then I would do that conversion of 2.54, and then I'd work that back up to meters. So you could do it that way as well. And so if you don't have this unit conversion handy, you can always fall back on one that you keep in mind, like 2.54 centimeters per inch. Okay, so that's how we came up with the 4.47 meters per second. And again, we're just trying to make sure that our units are all matching before we start using them in equations. What else do we know? Well, the axis of rotation is parallel to the surface of the water and is located halfway up the bottom of the hull. Now, why did we do halfway up instead of a third of the way up like last time? So a third of the way up is where we are planning for the water line to be. Why are we planning on a halfway up? So halfway up is probably a pretty good rule of thumb to think about where this is going to rotate. So even though the water line is a third of the way up, it still might rotate a little bit above that water line. And then the question is, well, how close is that? Is that going to be close enough? And so what happens if we used a third instead of a half? How much distance are we even talking about? And is that distance significant or not? And I would argue that the distance between a third of the way up and half of the way up is probably pretty negligible. And so having it rotate about half of the way up is maybe going to be a little bit more representative of reality. And even if it is off a bit, it probably won't change the performance of our boat too much. And so this is a call that the engineer has made, saying it's halfway up. And that's based on past experience. Okay, so the boat must maintain an angle less than theta and has these given dimensions. So these dimensions are the dimensions of that boat that I have sitting in my office, which is a store-bought boat. It's substantially larger than the footy class sailboats that you'll be designing and building. And so these dimensions will not match your scenario, but they are good for us to have an illustrative example here. So the height of the mast is this, the height of the hull is this, the height of the keel is this, and our angle is 30 degrees. So these are things that we know about our problem. What else do we know? Well, the mass of the ballast is approximately a third of the total mass of the boat. Wow, how did you come up with this, you might be asking? Well, this is another thing that is based off of experience, and we could probably go through and prove this out. It might be a little bit beyond the scope of this discussion, but if you wanted to, you could do that analysis. And so essentially, when we get done with this analysis, you could go back to our buoyancy analysis, and I suggest you do this, and look at what your total mass is that you are allowed in your boat and total all the components combined, and make sure that your boat will still float with the water line being about a third of the way up from the bottom of the boat. And now if you do that, and then you figure out how much of the mass needs to be in the ballast, I bet you'll figure out that it's about 1/3 of the total mass that you have available to get it to float a third of the way up. Okay, so this mass analysis, we are going to this sail area analysis that we're going to do today will become one of your appendices in your final report. So just like that, we did our buoyancy analysis, and so you could look back through and find what the mass of the boat is. So we calculated that out of, and we're just saying about a third of it's going to be the mass of the ballast. So we did that buoyancy analysis and came up with 1.49 kilograms. So a third of that's about 0.5 kilograms. What else do we know? Well, the boat is in static equilibrium, stationary in water, so the water's not moving relative to the boat, and the forces causing it to cause the keel to behave like an underwater wing can be ignored. And so if you think about it, we're not moving in the water. So if it was moving across the water, there might be a little bit of force on that keel that would be helping improve or decrease the angle at which the boat is listing in the water or tilting in the water. But we're going to say that those forces are so small, we can go ahead and ignore them. So what else do we know? Well, we know the total mass of the boat, which is the boom, the sail, the rigging. The reason we know that is because we are going to calculate that out. But if you think about the mass of the mast, boom, and sail and all the rigging, is that going to be a big number or a small number? If you think about the mass itself, it's probably going to be a pretty light member. The boom is what holds the sail in its shape. The sail itself is going to be light material, likely going to be mylar or a tent type material. And then all the rigging is going to be pretty light. So I'll bet we can neglect how much the weight is there. The center, because it's going to be such a small number compared to how much force we're going to generate by catching the wind with the sail. Okay, the center of mass of the hull, the rudder, the keel, the batteries, servo motors, they're located so close to the axis of rotation because we're going to have them down in here, right? Our batteries and our servo motors and stuff. And so if we think back to that moment arm is going to be so small. So when we take times a small mass by a really small moment arm, that's going to be a really small force or a really small moment trying to continue to rotate this boat. And so we're probably going to be able to neglect that as well. The center of buoyancy on the hull, the rudder, the keel, all of that's going to be pretty close to our axis of rotation. And so the center of buoyancy or the buoyancy force is going to be so close to the center of rotation, we will be able to neglect that as well. Wow, look how fancy that was. Okay, last thing that I think we can know is that the density of the ballast material is so much greater than the density of fresh water, we can probably neglect the buoyancy force on the ballast as well. Because if we have our boat kind of tilted in the water, there will be a buoyancy force that's acting in the positive direction, but we'll have the lead density is so much greater than the density of water that that buoyancy force is just going to be tiny compared to how much gravitational force there's going to be. So we can neglect the buoyancy force on that as well. The magnitude of the drag force of the sail, well, we know what this equation is. Think about it for just a minute and see if you can come up with this force of drag equation off the top of your head. We've seen it a few times now. I think this will be the third time that we've formally discussed it in class. Okay, so if you said 1/2 times the drag coefficient times the density of air, because that's what the sail is catching and experiencing, times the area of the sail times the velocity of the air squared. So how did we come up with this coefficient of drag for sails? Well, we said it's pretty close to a flat plate. So the drag coefficient that we defined before was 4/3. The density of air at 75 degrees, we looked this up on Engineer's Toolbox, and it is 1.188 kilograms per cubic meter. The area of the sail, well, this is what we're trying to find. So it's unknown. In the speed of the wind, we calculated that out, or it was defined for this for us, and then we converted it to 4.47 meters per second. Now, going back to this drag coefficient, well, if you remember, we talked about how things fly through the air and or how they experience what force is being imposed on them by wind. And so that's going to be dependent on the geometry and the orientation of that geometry relative to the wind. And so we have a bunch of different shapes here. And so you can see these drag coefficients. These have been empirically determined by doing a bunch of measurements. So you can see a flat plate is 1.17. And so we're a little bit higher than that. We're probably in this range where we've got this perforated semi-elliptical head going through there, 1.38. So we're somewhere in this range. We're saying that our sail is going to deflect a little bit when we are catching the wind. So this is like a downwind scenario. We've got our sail fully extended and it's just catching as much wind as possible. And it will deflect just a little bit, right? And so that's why we're saying it's a little bit better catching wind than just a flat plate. Because it's going to deflect a little bit, but maybe not quite as much as what we're seeing here in this semi-elliptical head. So that's why we say about 4/3. So that's our drag coefficient is 4/3. Well, what else do we know? The drag force is going to be applied to the sail a certain amount up the way of the mast. So if we think of a triangle, where is the most area that is going to be collecting wind? So if the wind is blowing directly at the screen right now, and this is the shape of our sail, we're going to be collecting wind in here. But really, if we were to resolve the amount of area there is in this triangle, there's probably a little bit more in the bottom third than there is in the top. And so that is what we're going to say is about 1/3 of the way up is where we're going to have our maximum amount of force. And so if we want to take all this area that's collecting this wind and we put it into a point force load onto our mast, it's going to be about 1/3 of the way up. We know a lot of stuff about this, don't we? So here's one more thing that we know about our scenario. The moment due to the force has this formula. Our mass times R cross F, but again, because it's perpendicular, we can say our R times our F. And the F is the applied force vector, and R is the position vector denoting the perpendicular distance between the axis of rotation and the line of action. So again, here's our line of action, and this is our axis of rotation, and so our force times our distance gives us our moment. So we know that equation. So how are we going to do this? Well, we're going to draw a free body diagram. Then we're going to calculate the moments due to the force of drag, and we're going to call that moment, or M sub d, and the force of gravity, M sub g. And we're going to determine the position vectors for the force of drag, which would be R sub d. So how far out are we pushing on it, or that moment arm? And then the force of gravity, which is the moment arm, or the distance away from the axis of rotation to the force of gravity. And then we're going to determine the force of drag, F sub d, and the force of gravity, F sub g. Since our boat is in static equilibrium, the sum of the moments acting about the center of rotation is 0, so that makes it a lot easier. We can sum up our forces and our moments and set them equal to 0 because we're in static equilibrium. This is a static case. And then we're going to solve for the area of the sail. So what does our free body diagram look like? Think about it for just a minute. Maybe even sketch it down on a piece of paper. Try to think about what this free body diagram is going to look like. Where are the forces being applied to our system? And can we simplify our system down into some points and lines? So this is a free body diagram of what we're looking at today. So we've got this line coming through here, and so this is kind of representative of our ballast would be at the end. We've got our keel up to our center of rotation, which is about halfway through the middle of the hull. And then from there, from the middle of the hull, all the way to the top of our mast. And so that's kind of what this line represents. And this point is the center of rotation or the hull of the boat. Okay, so now we've got our drag force. So this is wind blowing on our sail, and we've got this drag force, and it's going to have a distance away from our center point or our point of rotation. Same thing with our force of gravity. It's going to be pulling down on that ballast, and there's a distance away, and you can see that it's the perpendicular distance away from that center of rotation, and it's going to line up with our force of gravity that's put on there. So if we were to calculate our moment, we've got our force of gravity times our distance away from rotation, which is R sub g. So if we populate this, this is what our equations look like. We have our R sub d is in the y direction. So we've got our R is equal to H sub d cosine theta. So if we have SOHCAHTOA, the reason we use the cosine is because we know the adjacent and the hypotenuse angles of this H sub d. Now the force of drag we're going to have is this force of drag in the x direction. So that's pointing in the positive x direction, and so we've got our force of drag here. So the moment is going to be our distance vector times our force vector. So if we plug those in, we've got this equation right here. That's pretty easy for us to do, right? We've got our H sub d, which is this length here, times the cosine of theta. And so this times our cosine of theta is going to give us our R sub d. And so that's this line right here. This distance right here is what that value is. Now our force of drag, that's our equation for drag force. So we put that in, and so we simplify it back down, and we've got this expression right here is equal to our moment of the drag. So that is the moment being rotating our boat over in this direction. Okay, so the force of gravity, now we're looking at our ballast, and so we've got the same thing going on here. We've got our R sub g, and so we're trying to figure out, so looking at the triangle, this angle right here is the same angle as this one right here. And so if we look at that, we know what our hypotenuse is, which is our H sub g, and we know what our opposite is. And so we use the sine function. So our H sub g is the hypotenuse, and then the sine theta, this equation right here will return what the opposite side is, our R sub g, which is the distance away in the perpendicular direction from the center of rotation to our line of action, which is where this F sub g is being applied. So our F sub g is equal to negative our mass of the ballast times our gravity, because we have our force acting in this direction, and it is a mass times a gravity. acceleration. So the moment due to this is our moment is equal to the length times the distance, and so we end up with our length vector and our distance vector, or sorry, our force vector, and we can simplify it down into this expression. Hopefully everybody can follow that. Our mass of our ballast times gravity times our h sub g, which is how far away from that rotation point is down to where our ballast is, times sine theta. And that's in the z direction because we did our x cross our y and we're getting a moment around the z direction. So again, that's where the right-hand rule comes into play. We crossed our x and our y and we got a moment in the z direction. Okay, so if we've got a static equilibrium, we're going to sum up our forces, or sorry, our moments of the drag and the gravity, and we're going to set that equal to 0. So then we plug in those two equations that we just developed on these two previous slides. So this one here and this one here, we're going to apply those to this equation. We're going to plug those in, and we're going to be able to group the terms. So if we group the terms together of what's going in the positive and negative z direction and group what terms are together, then we will end up with this expression. Oh, geez, my mouse scroller button is too fine of resolution. Okay, so we're going to end up with this expression. So we're going to hold on to this for just a minute. Now, I suspect a few of you might be asking, well, why is this a negative number? And it comes down to the right-hand rule and thinking about which direction these are causing the moment to be in. So if we have our right-hand rule and we're looking at this, maybe if we go back to here, you can see that we have this is a positive cross this, and because of the direction that we are crossing them, we end up with the negative moment due to drag. And so this is a, depending on how you're looking at it, if you're looking at the paper, we've got a positive moment that rotates counterclockwise. So this is a positive and this is a negative. So depending on how you're looking at the boat or how you're looking at the screw head, you'll get either a positive or a negative. And probably the more important piece of this is that you know that they're opposite directions. So as long as you keep track of your signs, that's what matters the very most. So we can see that these are going in opposite directions, so that's why we're going to have a negative on one versus the other. Okay, so now let's look at the moment arm. We need to figure out what this h sub d is. Well, do we know what that is? How would we come up with that? We've got our hull height, so if we're talking our h sub d, that's going to be equal to a third of the way up the mast, so that's pretty easy to do. And then our hull height, we are assuming that this point is in the middle, so we could do our h sub h divided by 2, so it's halfway through the hull. So h sub d is going to be equal to half of the hull height and a third of the mast height. What about the moment arm of the gravity? About the same thing. We've got our keel height plus half of the hull height. Those are pretty straightforward, right? So that's what these two expressions are right here. So our height for the drag force is going to be the height of the hull divided by 2 plus the height of the mast divided by 3. The length of the moment arm for our gravity force, we've got our hull height divided by 2 plus our keel height. Okay, so let's go back to our moment equations. And let's just zoom out for a second and remind ourselves what we're trying to do. We're trying to maximize the sail area analysis and make sure that we don't tip over more than 30 degrees at 10 miles per hour wind. So if we have these two expressions here, we plug them in together. Now we can solve for this area of the sail. And so that's all we're doing here. We're putting these equations back together, and then we are solving for our a sub s. So we just rearrange the equation. So you can see that we flip this over and take these terms to the other side, and we take this term also goes over to the other side. So you can see we're just moving and rearranging. So this all goes over here, and then we flip everything else. We invert it because we're taking it over to the other side. We're dividing both sides by that, and that ends up leaving us with the area of the sail. So now we just need to plug and chug. We just plug in all the values that we have because we know all these variables in the area of the sail is 0.206 meters squared. So that is the maximum area of the sail that we can have in order to not tip over at 10 miles an hour. So this is just another look at it a little bit closer. So these are all the equations that we went through on one slide. And so you look at this in the beginning and you probably were maybe a little bit intimidated by it, but now that we've walked through it, you're like, oh, I can do this. This is pretty easy. We just need to step through it. And so that's one of the main points in engineering that is important to understand is try to break it down and start with that free body diagram. If you start with a free body diagram, then that, and you have it drawn out nice and clear, nice and clean like this, then you can just step through all of the different pieces and break it down into parts that are easily determined. Let's see here. I think that is pretty much all of it. So the only thing I wanted to say here is available on Canvas is an example. And there are two different examples because it's going to be a little bit different if you are doing it with a catamaran. Now think about the difference. What would the difference be with a catamaran? That's two hulls and no ballast and keel. So how can we get away with that? Well, as it rotates, the area of one of those holes that you have in the water, the area that gets pushed down into the water increases if we're thinking about a cross-section of a catamaran. As it gets deeper in the water, that area, the cross-sectional area, increases. And if you have it times a length, you've got a volume. And so as it pushes down in the water, as it tries to tip, that volume is increasing. And so you're actually increasing the buoyancy on that side. And so that's how you keep your boat from tipping over in the case of a catamaran. Whereas in a single hull design, you don't have that moment arm of a from the center point of a catamaran going out to the separate holes. That is your moment arm. And then the force that's being generated is the buoyancy force. And so as it gets pushed down in the water, you're increasing the force, and that force has a distance away from where the mast attaches to the boat. And so now you have an increase in moment that is helping keep that boat from tipping over. So a catamaran is a little bit different in that you're using a buoyancy force, and the moment arm is the distance from the pontoon or the hull over to where it's going to rotate, which is about where the sail would connect to that hull. Whereas a single hull design, you don't have that, and so you have to put a ballast at the bottom. And so think about the variables that you have to play around with in here to make your boat more successful. You could change how long your keel is. However, if you make it too long, it's going to drag on the bottom of the pool, which is not good. And the pool depth is about 13 inches. Now, if you think about 13 inches to here, you don't want to push that right at the limit because it might drag in certain areas of the pond because there's some wrinkles in the bottom of it. So if you went, your ballast is all the way touching, then you've got that distance from the bottom of the ballast to the top of the ballast. And then you have the keel itself. And then you have about a third of the hull, but what if your calculations are a little bit off? So maybe it's closer to half of your hull is down in the water. But this distance here on your keel height is a variable that you have. And so you can get away with a little bit less weight if you have a little bit longer keel. So again, the whole point is to try to get as much sail area as you possibly can for a fast boat. And so if you're maximizing this, you've got a couple of variables. You can increase the mass here, but if you increase it too much, now your buoyancy, you're not going to be at a third of the hull, you're going to be closer to a half. So just think about the variables. You're trying to maximize the force that can generate on your sail, and you've got a few variables that you can play around with. So put that into your Excel spreadsheet or your SMath or your MathCAD sheet and work through it. Try some different variables and try to optimize this system. That's really what we're trying to do here. Last thing I'll say is there's a MATLAB code. If you'd like to use that as a starting point for your analysis, that's totally fine. So we've got a good example of what you should do for this assignment and turn in. and this is going to be an appendix in your final report, so do a good job on it. And then also we have examples. The only thing that I was trying to show here, and I didn't talk about it, and we'll talk about it a little bit more later, but the attached flow, there's this, the flow on a airfoil stays attached if this attack angle is below a certain number, and also that this angle on the backside is below a certain number. So you can see once you start getting too high of an angle of attack, you start getting separation of the flow, which means you're no longer generating lift. And so this is a stalled configuration. So we'll talk a little bit more about this when we start designing, when we start talking through our sail itself and the flexibility of it. Okay, hopefully this was helpful in understanding how we can get the maximum amount of sail out of our sailboat.